Hello everyone, I'm Sandra Sandosh from 3rd Sem C section and today I'll be presenting on peak detectors. This is a topic that comes under module 1 which has to do with BJT biasing and applications of op-amps. Peak detector is one of the several application circuits of op-amps. It is a circuit whose purpose is to tell us the peak value of the input signal in a circuit. A positive peak detector captures the most positive point of the input signal and a negative peak detector captures the most negative point. Ideally, the output of a peak detector tracks the input voltage until the extreme is reached and holds on to that extreme value even as the input decreases. We know that in AC circuits, the applied signal has a varying value, and for sinusoidal waveforms, we consider its RMS value for general applications. However, the RMS value is somewhat of an average, and sometimes we need to know what the maximum value of the waveform is. Cases like when devices have a voltage limit, past which voltage can cause damage or malfunction. This is where the peak detector comes in. The basic form of a peak detector is made by using a diode and a capacitor in series connection. However, Module 1 is about op-amp applications, so we need to know how to set up a peak detector by making use of an op-amp. An op-amp peak detector circuit consists of diode and capacitor along with op-amp. No other complex components are required. The diode is used to accept only positive wave of the signal or only negative wave, depending on which extreme is being tracked. Capacitors charge the maximum value of any applied signal, and that is how we get the output of the peak detector. Op-amp acts as a voltage follower and buffer and prevents loading effect caused by the drop in potential. What is the loading effect? When a component having some internal resistance is connected in parallel with the load resistance of circuit under test, the circuit conditions will be altered. The effective resistance will be the parallel combination of the two. And as we all know, parallel combination always gives lesser resistance than either of the two resistance. The voltage across this effective resistance will also appear to be less than the true voltage. This is known as loading effect. Hence, to prevent this, the component must possess a high input impedance. And the ideal characteristic of op-amp is to have infinite input impedance, which is why we use it to prevent the loading effect. Having gotten the definition and the necessity out of the way, let's take a look at the peak detector circuit. This is a basic peak detector circuit which can be used to detect the positive peak of signals. This circuit has an op-amp, which is an integrated circuit that is designed to perform mathematical operations such as amplification and comparison on input signals. The working principle of the circuit is that the peak of the input waveform is followed and stored in terms of voltage in the capacitor. As time goes on, if the circuit detects a higher peak, the new peak value gets stored in the capacitor until it is discharged. The capacitor employed in the circuit is charged through the diode by the applied input signal. If we ignore the small voltage drop across the diode, which is the cutoff voltage, which is roughly 0.7 volts per silicon, we will get about the same as the peak of the input signal at the capacitor. If we consider initially that the capacitor is charged to some voltage Vc, the diode employed in the circuit gets forward biased when the applied input voltage Vn exceeds the capacitor voltage Vc. This allows the circuit to behave as a voltage follower, and the output voltage follows the applied input voltage until Vn is more than Vc. As the input voltage Vn reduces below the value of the capacitor voltage Vc, it causes the diode to get reverse biased, as the capacitor is on the other side of the diode, and when capacitor voltage is higher, the diode gets reverse biased. In this condition, the capacitor retains the value it was previously holding until the input again exceeds the value stored in the capacitor. So this is the working of a basic peak detector circuit. However, we also use an improved peak detector circuit to fix some issues that happen in the basic peak detector circuit. In this circuit, as we can see, there is one additional op-amp and one diode. The second op-amp, which is A2, is part of a buffer circuit. The first op-amp provides a high impedance load in order to prevent loading effect, and the second op-amp performs a buffering action between the load and the capacitor. This circuit has the same basic principle as the basic peak detector. However, the difference with the improved peak detector circuit is that if the input moves from positive to negative, the, uh, the diode D2 employed here, it restricts the output of op-amp A1 from reaching negative saturation. This also provides us an improvement in the recovery time of op-amp A1. What do we mean by the recovery time of an op-amp? It refers to the time it takes for an op-amp to recover its ability to amplify signals after its output voltage has been distorted by applying an input that exceeds its rated values. If the input signal exceeds the op-amp ratings for any amount of time, we need to ensure it recovers quickly in order to continue its working, which is why it's important to either keep the voltage within the rating or to improve the op-amp's recovery time when subjected to such voltage. Because we are using an AC signal, we can't always say whether the applied voltage will remain within the ratings of the op-amp. So in the improved peak detector circuit, we employ an additional diode in order to make sure that even if the signal exceeds by a bit, the recovery time of the op-amp will be such that it will not cause any harm to the circuit. Also, in this circuit, we have two resistance R1 and R2. We will always take their values to be same so that the effect of the offset voltage of the op-amp will be prevented. Having seen these two circuits, let us look at the output and input waveforms of the op-amp. In this, the blue line represents the input, which is a normal sinusoidal wave, and the yellow line represents the output, which is the capacitors charging and discharging. As we can see, although there are some variations, more or less the output waveform matches the peak value of the input. Hence, by using the peak detector circuit, we can get the peak value of any applied signal. Let us discuss some applications of op-amp. It is used in the analysis of spectral and mass spectrometer. It has its applications in destructive testing. It is used for instrumentation measurement, mostly in amplitude modulated wave communication. It finds application in sound measuring instruments. It is used in audio processing, power supply monitoring, and radio communication systems. It is especially useful in applications where a fast and accurate measurement of the peak value of an input signal is required. The performance of an op-amp peak detector can be optimized by selecting the appropriate values for its components such as its reference voltage, its load resistor, and its storage capacitor. When we want the peak detector to be fast, we can make use of a larger load resistor and a smaller storage capacitor. If we want the output of the peak detector to be more stable, we can use a smaller load resistor and a larger storage capacitor. This is a trade-off between speed and stability of the op-amp. We consider these three components for an op-amp performance because the reference voltage determines the threshold at which the peak detector starts to detect the peak value. The load resistor and the storage capacitor determine the speed and stability of the peak detector. Hence, by taking care of these mentioned components, we can adjust the performance of the op-amp to fit several applications. In conclusion, an op-amp peak detector is a useful and versatile type of peak detector circuit that can be optimized for different applications. It is an essential component in many electronic systems, and its popularity is due to its accuracy, speed, and ease of use. Thank you very much for listening.